Welcome back to Applied Mathematics. In this video, I want to talk about standards of measure. In a mathematics course, we are very happy to deal with numbers as abstract concepts, something of interest in a purely abstract sense that has no physical meaning whatsoever. But mathematicians are weird, and there is no one else in the world who is interested in any way, shape, or form of doing that. So instead, we tend to use numbers attached to some sort of unit of measure in order to describe something in the world. The simplest measurements are those of counting. I can go through my roster and count the number of students who are enrolled in this course. I can dig through my desk drawer and count the number of pencils that I have laying around completely worthless and unable to be sharpened further, which is more than I probably want to admit on this video. But counting things gives us a sense of measure, but doesn't help us for a lot of things. The great advancements of human society have come on the heels of understanding new things to do with numbers, right? Counting was the first one. Being able to describe the number of chickens that you were going to trade with your neighbor and the number of bushels of wheat you were going to get in return. Then architecture. Being able to describe the size of a building, length, width, and height. There's no way to do that with just numbers. Instead, we needed to find something else to count. And what we counted were multiples of some standard, starting with some sort of a rod of a finite shape. We can just lay it down, pick it up, put it down again, pick it up, put it down again, and count how many of these rods go across in a space. Subdivide that, talk about ways of describing multiples of them, the measurement of the foot, literally the length of a human foot. Then that got to be a little bit cumbersome because if you've never noticed, people's feet come in different sizes. And so a new measure was established called the rod, which was a very mechanical way of averaging people's feet. Take 16 men of the village and have them stand heel to toe. That distance is a rod, cut it in half, and again, and again, and again, and you have 16 feet. And those kinds of standards have been used for a while. We got a little bit more standardized. There is an artifact in a museum in England called the Yard. It is a bar made of solid gold, and given the right atmospheric conditions to deal with thermal expansion of materials, the yard is exactly 1 yard long and has a cross section that is a square that measures exactly 1 inch by 1 inch. It is the only thing in the world that is exactly 1 yard long, and it is the only thing in the world that is exactly 1 inch wide. It is the definition of the yard and the definition of the inch, or at least it was for a while. In modern world, we base everything on a scientific measurement. The meter is defined as the distance that a photon of light can travel in a certain period of time having to do with the radioactive decay of, I believe, cesium, but I'm not 100% on that. And then the yard is defined as 0.9144 meters. The yard is a metric unit. It's just a very stupid metric unit that no one can think of using. So we've had these propagations of tooling and of measurement ideas. In the US Customary system, we start with the inch, then we have 1 foot, which is 12 inches. We have 1 yard, which is 3 feet. We have 1 mile, which is 5,280 feet. And unfortunately, because we live in the United States, yes, you do need to have those memorized. There is also, in the metric system, the meter. And you have that 1 meter is 100 centimeters. 1 meter is 1,000 millimeters. And you have that 1,000 meters is 1 kilometer. Once again, I expect that you have those memorized, or if you don't have them memorized, you have them on a handy reference sheet that you can keep with you as you are working on things in this course. There is, as I said, a conversion between US customary and metric units. If it all talks about length, there has to be a way of doing it. Those ones I do not expect you to know offhand. There are all sorts of other weird units of length in the US customary system, right? The rod, the furlong, I'm blanking on a couple of the other weird ones, but again, I don't expect you to know those. I expect you to know these. Liquid volume, the US customary system really goes crazy because there are so many different applications of needing liquid volume, and all of them developed their own systems of measurements. I'm going to start with the smallest, which is the teaspoon. And 1 tablespoon is 3 teaspoons. 1 fluid ounce is 2 tablespoons. 1 cup is 8 ounces. 1 pint is 16 ounces, which, yes, that's the same thing as 2 cups. Likewise, 1 cup is 16 tablespoons. 1 quart is 4 cups. And yes, that's the same thing as 2 pints. 1 gallon is 4 quarts. And again, you can keep going from there. There is the hogshead, there is the demijohn, there is the barrel, there is the keg, all these larger units of volume. Why do we have all of these? Because we do, and there's no getting around it, I guess. Unless we were anyone else in the world, that just goes with the liter. And you can take 1 liter and divide it up into 1,000 milliliters. If you have a lot of liters, I guess you could break them into kiloliters, but I've never seen an application of that much liquid. 1 liter is approximately on the same size as a quart, right? 2-liter bottles, 1-liter bottles, half-liter bottles of beverages are fairly common in the US these days. But again, just We have what's happening in the United States, and we have what's happening everywhere else in the world. When it comes to weight, things get even weirder. In the US customary system, the units of weight are the ounce and the pound. And yeah, there's the ton as well and a couple of others, but I don't want to get into it. There are, in fact, 3 different weight ounces, but I'm going to stick with the one that's standard for culinary use and not worry about the other ones. At least one thing that makes sense. There is an ounce of weight. There was also a fluid ounce for liquids. And it seems odd that we need both of these, but they are in fact the same measure. In fact, an ounce of weight is defined as the weight of 1 ounce of water. And the pound of weight is defined as the weight of 1 pint of water. A pint is a pound the world around. All right, so something about the US customary system makes sense. There's also a rule. 1 gallon is the amount of liquid that can be held in a box that measures, I think, 231 cubic inches, but that's why, I don't know. Here's where things get weird. In the metric system, there actually is not a measure of weight. Instead, there is a measure of mass, which is the gram, and then you can have milligrams. 1,000 milligrams makes 1 gram, and you can also take 1 gram, you can take a bunch of grams, 1,000 grams, and make them into 1 kilogram. The nice thing about the metric system is that the conversions are all the same. If you put an M in front of the unit, that means you divided it into 1,000. If you put a K in front of the unit, that means you multiplied it by 1,000. All right, there is a distinction between mass and weight. Weight is an effect of gravity. You may have heard at some point in your life that you would weigh 1/6 as much on the moon as you do on Earth. Mass, on the other hand, doesn't have that distinction. If you are 100 kilograms on Earth, you are also 100 kilograms on the moon, which has its benefits, has its drawbacks. Simple idea in physics, Newton's law of universal gravitation allows us to convert between mass and weight in a convenient way. There are units of mass in the US customary system. They are called the grain and the slug. There are units of weight in the metric system. They are usually the Newton, but those are never used in those contexts, so we're not going to worry about them. In the US customary system, we talk about weight. In the metric system, we talk about mass. There is a distinction between them. This is not a physics class, so I don't care all that much about it. The last thing that I do want to mention in this video is the relationship in the metric system, which makes a lot more sense. 1 milliliter of a liquid is the amount of liquid that fits into a box that measures 1 centimeter on each side. The mass of that liquid, if it is pure water, is 1 gram. So there is a very natural link between the meters, grams, and liters in the metric system. There are sort of some links like that in the US customary system, but not too many. These conversations almost always lead to a question of, well, if the metric system is so much easier, why is the United States insisting on sticking with the archaic system that we have? There are two answers to that. The first one is that the US customary system is a lot more convenient in the sense that we very often do not need decimal numbers. We more often need fractions, and based on students' responses every time I say the word fraction, I'm not sure why that's a point in favor, but the fact that the US customary system works with fractions and not decimals is one of the big reasons that it's kept in favor. The other reason is one of practicality. Because in fact, the United States did switch to the metric system in the mid-1950s. And then we realized how much it was going to cost and decided not to actually do anything with that change and just redefined the yard in terms of a fraction of a meter and said, okay, that's the metric system. The reason that the world was able to agree on a single type of unit of measure is, odd as it seems, the destruction of World War II. Most of Europe was destroyed in the fighting in World War I and World War II. And yes, military targets were the prime targets of bombings and raids, but after direct military targets, the next important targets were manufacturing targets. So the giant machines that make things, many of you taking this class, many of you studying this, are looking at careers in carpentry, in machining, in welding, and so on. So I want you to think about a machine shop, the giant lathe and the mill that have dials down to the nearest thousandth of an inch. Sure, you can convert from US customary to metric on most machines that have a digital readout today, and it works. But it doesn't really, right? You can move the table on a mill by 1/1000th of an inch. If you convert that into metric, it's something like 2.4, or I'm sorry, 24 microns. So you can go 24 microns or 48 microns, and going somewhere in between is much more difficult. The mills and the lathes that are used in manufacturing in the United States are based on US customary system. More important than that, the tools that make those lathes and those mills are built around US customary tolerances. And they have been for centuries. We don't want to start from the ground up. Europe had to start from the ground up in the late 40s and early 50s. There was no manufacturing left. They had to build new things. And leaders of European nations got together and said, well, why don't we just all use the same thing? Scientists really like this metric thing. Why don't we go with that? At the same time, Japan likewise destroyed. China still starting to develop its manufacturing. The Middle East didn't really have any manufacturing yet, looked around, saw that all the world was doing this metric thing, and they joined in as well. So in a sense, the United States, being isolated from the conflict of World War I and II for the most part, is the reason that we have such difficulty switching over and joining the metric system, for better or for worse. A whole lot of vocabulary and terminology, lists of things to memorize or have available on a formula sheet. We'll play around and use those in the next video. For now, as always, thank you for joining me.